Hey everyone and welcome. Today we're going to peel back the layers of C programming to see what's really going on under the hood. We're going to start with the tiniest little switches inside your computer and build all the way up to making your code smart. Let's start the journey.
It all really boils down to this one big question, right? We see programs making choices all day, every day. But how does a hunk of metal and silicon actually do that? How do you teach it to make a decision?
Well, think of it like we're on an architect's journey. First, we have to get comfortable with our most basic tools, the switches, the bits themselves. Then, we need to learn the blueprints, the absolute unbreakable rules of the language. And only then can we start designing programs that can actually think and choose for themselves.
So our first stop is the absolute ground floor. We're talking about the one and only language your computer hardware actually understands, the language of on and off, of zeros and ones.
That's right. It's kind of an illusion. The numbers and characters we see are just convenient for us humans. For the machine, it's all just a pattern of zeros and ones. And that's where Bitwise operators come in. They are our surgical tools. They let us get past the fancy stuff and directly manipulate those raw bits. It gives you some incredible power.
Our first tool is the Bitwise AND. Now, I want you to picture a long row of light switches, but there's one master switch at the end. That's the AND operator. If that master switch is off, a 0, it doesn't matter what the other switches are doing, the light stays off. This is exactly how we can mask out certain bits and force them to be 0.
Next up, we have Bitwise OR. And if AND was the master lock, this one is the emergency override. If the override switch is flipped on, a 1, that light is coming on, period. I don't care what the other switch says. And that's what we use it for, to set or force specific bits to be on.
And then, there's my personal favorite, XOR. It's like those two-way switches you have on a staircase. The light is only on if the two switches are in different positions, one up, one down. If they're both up or both down, the light's off. And this unique little property, well, it leads to a really cool bit of programming magic.
Here it is, the classic interview question, the party trick for programmers. How in the world do you swap the values of two variables, let's say A and B, without using a third variable to temporarily hold one of the values? The secret, as you might have guessed, is all in the weird logic of XOR.
Okay, let's walk through this. Let's say A is 5 and B is 9. Step 1, we XOR them together. The variable A now holds this new combined value of 12. It's like a temporary mix of both numbers. Now step 2, we XOR this new A with the original B. Because of how XOR works, it basically cancels out the B information, leaving B with the original value of A, which was 5. Magic. And for the final step, we XOR our mixed up A with the new value of B. This cancels out the original A part, leaving A with the original value of B, which was 9. They're swapped. And look, this isn't just a trick. In places like graphics or embedded systems where every single byte of memory is precious, this is a beautiful, efficient little dance that saves you resources.
Okay, so we've mastered our tools, but any good architect will tell you, tools are useless if you don't understand the blueprints, the fundamental rules that dictate how everything has to fit together. Without them, you just have chaos.
Just take a look at this expression right here. 10 plus 20 times 30 divided by 10. If you just read it left to right, you get 90. But if you remember your math class and do multiplication and division first, you get 70. So, which is it? A computer can't guess. It needs a strict, non-negotiable set of rules to follow every single time. And that is exactly what operator precedence is.
Now, the full precedence table can look super intimidating. I get it. But you can just think of it like a pecking order. At the very top, you've got the groupers, parentheses. They're king. They always go first. Then comes the heavy machinery, multiplication, division. After that, you've got your everyday math, addition and subtraction. And way down at the bottom of the list is the assignment operator. It's pretty much the very last thing to happen.
But wait, what happens when operators are on the same level, like multiplication and division? Which one goes first? Well, that's where associativity comes in. It's the tiebreaker. Most of the time, it's just left to right, the way we read. But you gotta watch out for a few right to left rebels. The big one is assignment. That's why a line like A equals B equals 5 actually works. It assigns 5 to B first and then assigns that result to A. It goes backwards.
All right, this is where it all comes together. We have our tools, the bits, we have our blueprints, the rules of precedence.
Now it is finally time to use all that to design programs that can actually make decisions. Okay, so the if statement is your most fundamental decision maker. I want you to think of it like a security guard standing at a door. The guard asks one question: is your condition true? And in C, true just means any value that isn't 0. If it's true, the guard opens the door and lets you run the code inside. If it's false, meaning it's exactly 0, the guard just says nope, and you skip right past that block of code.
Now, when you start nesting these if statements, you can stumble into a classic C trap, the dangling else. Just look at this code. The way it's indented, it looks like that else belongs to the first if statement, right? But is that what the compiler sees? That little bit of confusion can lead to some really nasty bugs in your logic.
And here's the rule that clears it all up. C doesn't care about our pretty indentation. It has one simple rule: an else always pairs up with the nearest if above it that doesn't already have its own else. So in our last example, that else actually belongs to the inner if. The takeaway here is so important. Always use curly braces to make it crystal clear what you mean.
So what happens when you have more than just a simple yes or no? You could build this long, clunky chain of if-else-if statements, but C gives us a much cleaner and often faster way to handle it when you're checking one variable against a whole list of specific values. I call it the vending machine choice.
This table lays out the difference perfectly. The if-else-if ladder is like a security checkpoint. It has to check your ID, then check your bag, then check your ticket, one by one, in order. The switch statement, though, is a vending machine. You punch in B4 and it jumps directly to B4 to give you what you want. No checking A1 through B3. It's way more efficient for that specific job.
But, and this is a big but, the vending machine has a trap. If you forget to add a break statement at the end of your choice, the program does something called falling through. It executes the code for your choice, and then it just keeps going, and executes the code for the next choice too. It's like the machine gives you your chips and then the candy bar right below it for free. Sometimes that's useful, but most of the time it's a bug you didn't mean to create.
So there we have it. We started down at the level of raw bits. We learned the unbreakable blueprints of precedence, and we used them to build logic that lets our code actually make a choice. We've completed the architect's journey. You now have the fundamental building blocks to create smart, efficient, and powerful code. So the only question left is, what are you going to build?